All right, so what we're going to do now is we're going to talk about differentials, which will pretty much finish up section 11 of chapter 3. Now, the one comment I want to make about differentials is that it pretty much says, look, we're going to do the same thing as linearization, but instead of finding the equation of the tangent line, what we literally need is just the slope of the tangent line. Because if I have the slope of the tangent line, and I know what point I'm starting from, then I know how much I need to move right, left, up, or down, just using the fact that the slope is rise over run. So to define what differentials are, so just keep in mind that differentials and linearization, they both do the same thing. Linearization uses the equation of the tangent line to approximate the y values of the function. Differentials starts at the point of tangency and then uses the slope of the tangent line to tell you how much to move up or down when you move a certain amount to the right or to the left. Okay, so by definition, here's how we would define differentials as. So if y equals to f of x and f is a differentiable function, then the differential with dx as the independent variable and dy as the dependent variable is, so let's start off with this. What we have is we start off with y equals to f of x. And what do I know? If y equals to f of x is differentiable, then what I could do is I could say, well then, dy dx is equal to f prime of x, right? So I basically found the derivative on the left side and the right side. So here's my derivative, which is what I want to use for differentials. But here's what we do. Since this is dy over dx, which this is what? The change of y divided by change of x. If I multiply both sides by dx, what happens is these dx's cancel out. And what does that give me? This gives me that dy equals to f prime of x dx. And by definition, this is my differential. Why is this my differential? See, dy is how much your y on the tangent line changes. Dx is how much the x on your tangent line changes, or how much we move right or left. So f prime is the slope of the tangent. Dx is how much I'm moving away from the point of tangency. So what we're basically saying is, think of it this way. Since f prime is the slope of the tangent, think of it as rise over run. That's what a slope is, right? And dx is basically how much we're moving in the horizontal distance, how much we're moving to the left or to the right, which this is pretty much our run. So think of it this way. I'm grabbing the rise over run, I'm multiplying to the rise over run by run, which what happens to these? They cancel out, which then I'm left with how much I should rise, which means move up or move down. So basically, this dy, which is telling me how much I should move up or down from the point of tangency, depends on f prime of x times dx, which is the slope times how much I'm moving to the right or to the left. So let me just kind of draw a picture that describes what's going on here. So picture that describes this is as follows. So imagine that we have a graph that looks like this. So let's go with a red graph. Okay, that looks like that. So this is what? This is my f of x. Okay, and then we have a tangent line, and let's call this the point of tangency. So there's my tangent line. So basically, here's what differentials does. If this is my x value, which is my starting value, if I want to use the tangent line to approximate the y value of this function, let's say here, what do I notice? Let's call this distance the horizontal distance. Let's call that delta x, which is basically to go from this x value to this x value. The red graph, the x value changed by this much, which that's the change in x, which is my delta x, okay? And then, of course, for the purple graph, what do you notice? In terms of the derivative, the change in x from this point to this point, which is my horizontal distance, we're going to call this distance dx, which how much my tangent line changes by in the x direction. So delta x is how much the original curve, how much the x value changes by from here to here is what we're calling delta x. Now dx is how much the x value changes, or what my run is from this point to this point on the tangent line, or on this purple graph, which what do you notice here? Dx and delta x end up being the same thing, right? Because from this point to that point, the amount that my x changes by is the same, which is this distance, which is the same as how much my x changes by on the red graph from x to this point. So right here, delta x and dx end up being the same thing, okay? However, what's delta y described as? Delta y is going to be the change in y on the actual curve, which is basically from this point to that point is my delta y. And what's dy going to be? Dy is going to be the change, or the point from the distance from the point of tangency to the point that I'm using to approximate the y value of this function. So this is actually dy, which dy tells me from this point to this point how much my y value increased by in this case. Okay, so once again, we're using this point to approximate that y value of this function. But what we're saying, or differentials just says, look, if you start from this point, if you move dx to the right, then you have to move up a distance of dy, which that's what this tells me, this formula. So dy tells me how much I should move up or down starting from my point of tangency. Okay, so we're going to put that to use. So let's actually let me just kind of summarize this visual, with this picture, with what's going on, and then we'll do an example, and that'll basically do it. So what we could say is that dy represents the amount that the tangent line rises or falls when x changes by an amount of dx. And then we could say, and delta y is the amount that the curve y equals f of x rises or falls when x changes by an amount delta x. But in this case, remember, delta x and dx are the same thing. It's just the delta y and the dy that are going to be different. So let's do an example. And then once we're done with this example, we'll be done with this section. So example 1. So here's what we're going to do. We're going to compare the values of delta y and dy if f of x equals to x cubed plus x squared minus 2x plus 1. And x changes from 2 to 2.05. So if you think about it, what are we doing here? We're starting from the x value 2, which the point on this curve at 2, so let's do this. F of 2 is what? 2 cubed plus 2 squared minus 2 times 2 plus 1, which what does that equal to? That's 8 plus 4, which is 12, minus 4, which is 8, plus 1, which is 9. So what am I doing here? We know that the point 2 comma 9 is on this curve. And we want to use differentials to approximate the y value of this function when x is 2.05, okay? And then what this question is saying is, it's saying compare delta y, which is the actual change in the y direction from 2 to 2.05 of this guy, and compare it to dy, which dy is the approximation of how much this function changes in the y direction from 2 to 2.05. So I guess the differentials part will be extra, but we'll do it anyway just to kind of see what's going on. So what do we know? By definition, differential is defined as dy equals to f prime of x times dx. Okay, so what's dx? Well, dx is just a change in x, which what are we doing? We're going from 2 to 2.05. So dx will be what? 2.05 minus 2, which is 0.05. Okay, and the next thing we need to find is what? F prime of x, which f prime of x is going to be 3x squared plus 2x minus 2. And now what I need to do is I need to find the slope of the tangent of this guy at x equals to 2. So to find f prime of 2, that gives me 3 times 2 squared plus 2 times 2 minus 2, which is 14, I believe. Let's see, 4 times 3 is 12, plus 4 is 16, minus 2 is 14. So here's what we're claiming. Using differentials, what's dy going to equal? Dy will be 14 times 0.05. And 14 times 0.05 gives us 0.7. So what is this saying? What is this differential saying? If we move a distance of 0.05 away from 2, if we move 0.05 to the right, then my graph, or f of x, will roughly, the y value will increase by an amount of 0.7. So remember, we're still using the tangent line, so it's an approximation. So here's what we're claiming. We're saying since 2 comma 9 is on the curve, using differentials, what does this imply? When x is 2.05, my y value will increase by 0.7, which means my y value will be 9.7. So in other words, what are we claiming? We're saying that f of 2.05 is roughly 9.7. Now remember, this isn't exact because we're using the tangent line to approximate the y value of that function when x is 2.05. But you see how we're just using the tangent line, the slope. We're not using the equation of the tangent line, which is what we did yesterday. Okay, now let's compare delta y and dy. Dy we already found. Dy was 0.7. So we're saying the function will roughly rise by 0.7. Now delta y is the actual amount that the function changes by from 2.05 or 2 to 2.05. So to find delta y, what do I need? I need f of 2.05, which is the actual, which I'll plug into the function, minus f of 2, which is going, so this is the true change in the y direction, where this is the change of the y on the tangent line. So to find f of 2.05, I'm going to use my calculator, and let me get rid of these guys, and we'll plug in the function, and we'll use a table to find it. So the function we're trying to find is what? X cubed plus x squared minus 2x plus 1. So if I go to my table, and what do I want to plug in? I want to plug in 2.05. So when the x is 2.05, we get 9.7176. So this becomes 9.7176. Now notice how my approximation was actually pretty close to the actual. How come? Because we didn't move too far away from, if you look here, we didn't move too far away from 2. Remember, as long as you stay close to the point of tangency, your tangent line will do a good job of approximating the actual y value of this. So this will be 9.7176 minus f of 2 we found earlier was 9, which what was the actual delta y, which becomes 0.7176. So what is it that we approximated? We approximated that the y value will roughly change by 0.7, but in reality it changed by 0.7176, which is still a pretty good approximation. Reason being, we didn't go too far away from the x value 2, right? We only went a distance of 0.05 to the right. Now, if my delta x was larger, if I moved further to the right, then dy would not be as close to delta y. So there would be a greater difference between dy and delta y. Okay, so that basically wraps up this section. Feel free to ask me any questions that you may have, and then we'll take some more questions or work on more problems in class.